I will give you a signal that you have 3 minutes left, and you will tell us about the optimization of the observing strategy for COLIBRI. You can start.
Okay, so hello everybody. My name is Robin Marron. I'm an intern at the LAM, and I'm a graduate student currently in my last year at École Centrale de Lyon, which is an engineering school. So my work was focused on the observational strategy for COLIBRI. The idea is to determine the best strategy to detect at least 90% of the GRBs, and after detection, give an estimation of the photometric redshift with a maximum error of 5% within the 5 minutes after SVAM trigger. So what do we have at our disposal for that? On the right, you can see the transmission curves of the different filters and the reported on the three optical lines of COLIBRI. So the idea was to divide the strategy on 2 steps. The first step, of course, is the detection, and after detection, the photo redshift estimation. The parameters we could play with are the filters, which are GRI, ZY, the combination of GRI and ZY, and in the infrared, the J and H filters. And the other parameter, main free parameter, was the exposure time for each filter. So for the detection, I did the test on those GRBs, which are real GRBs, and that were kindly given by Damien, thanks to his GRB database that he just talked about before my talk. So these were the GRBs we tested on which we tested the GRB detection phase. Only 3 of them are what we could say high redshift, at least more than 4, a redshift of 4. This is an example of what the tests are giving for 1 GRB. So the idea is for a long time after trigger, we look at the SNR that the COLIBRI would have with those filters. For here, the example is with 5 seconds of exposure time. So we can see that for the first hour of observation, all the filters are above the threshold of SNR equals 5, which means that with no matter the filter, before 1 hour, we would have detected the GRB with our criteria of SNR above 5. The idea here is to see which filters are the best and see if the tendencies are changing along time. And we can see, for example, here that on the first half observation, the H filter is above all, but then the GRI filter gets better. So we can see that the best filter is not always the same along time. And on the right, you have the light curve, so the real data of this GRB, which are extracted from the database from Damien. But overall, on all the GRB tested, we could detect all of them with all filters at the first instant, 10 seconds after trigger. So to sum up the result of this test, you can see on the right for each optical line of COLIBRI, which filter is the best, and the mean SNR that we have with the 5 seconds of exposure time and 10 seconds after trigger. So the idea is for each line to take the best filter, of course. So we would take GRI for the blue line of Drago B, the ZY line for Drago R, and the H line, the H filter for the infrared line. So the idea is to conclude on this strategy for the detection phase, which means staying on GRI for B, ZY for R, and alternate between H and G for infrared, because we see that they are very close here concerning the position. And so that's it for the detection phase. Then I worked on the estimation phase. So just to notice that chronologically during my internship, I started with this phase, which explains later why some of the results will seem different. I will explain. So here is just a repartition of the parameters we used, because for this phase of the test, we didn't use real GRBs, but simulated GRBs using the empirical model. So here is the formula for the empirical model and the different parameters. We took the repartition from different literature, as mentioned here, the afterglows of sweet hair, gamma ray burst, this paper. So this is a repetition of the parameters. Here are, so it's a bit messy to look at first. It's just to present some of the tests I made. So you can see in red that for the 4 first tests, I used the default strategy we can see on the corner. This was the default strategy at the beginning of my internship. In the orange, we defined the filters for the detection and then the filters for the redshift estimation. So on the first 4 tests, we only we only change the exposure time. You can see in the first red square that we are changing the exposure time. And on the second, the 4 other tests, we are changing the filters we put for each exposure time. So for example, we try on test 11 only with wide bands, and then on test 13 only with short bands, just to see if the results will vary a lot. And this is the conclusion of these tests. So how to interpret the colors. When the color is tend to the red, it means that the result is higher than go far from 0. And when it tends to the blue, it means that it goes beyond 0. So the better is for the result is to stay around 0, because what we are depicting here is a difference between the estimated redshift and the simulated redshift. So we want it to be 0 ideally, but it's always not possible. We can see from those results that the test 10 gives the best results, because we have result close to 0. The graph shows a graphical view of test 10, where all we can see most of the points are aligned on the line, which means where the estimated redshift is equals to the simulated.
3 minutes, Robert.
Okay, thank you. So what we can see first is that the result is really good for the GRBs for which the redshift is between 3 and 8. And before 3 and beyond 8, the results are a little more messy. We have values that are not really aligned with the Z estimated Z equals simulated Z. But in the end, what we can see is even the other tests give quite good results, because we only have a difference of 1 value for the redshift, even for tests 7, 8. So the result is that pretty much all the strategy gives a good result, but if we want the best result, because the idea is to optimize the strategy, we would prefer test 10, and test 10 was the test with wideband. And yes, and test 14 is also good. So at the conclusion, we now have a conclusion for the second phase of the strategy, which is the redshift estimation phase. And for this, we will alternate narrow bands, because this is what test 10 was made of. First wide bands and then short bands for test 10. And for 10 seconds of exposure each. In this order, I, R, and G and J, because we showed during the detection test that I is better than R, that is better than J. Same for Z and Y. And the idea is to alternate the 3 bands, and to at the end have the higher SNR on each band and have more points to fit the model, and then estimated the redshift. Something I didn't mention for the detection phase, but of course we can stack the images. If at the first 5 seconds of GRI exposure, we don't have good enough SNR to detect, we can stack. We can do another 5 seconds of exposure and stack the image to until we have a conclusive SNR. And this can also be done on the estimation phase in order to have the best SNR for each point, and then fits the curve and gets an estimation for the redshift. So thank you for your attention. And I hope I didn't speak too fast. I realized I was speaking quite fast to be sure to be in time, but I'm listening to your question.
Thank you very much, Robin. So there is a question by Alan Watson. Alan, can you ask your question, please?
Yeah, sorry, I had to leave briefly to deal with something here, and I didn't quite get to the early part of your talk. I'm not surprised by some of your results, but I am a little bit surprised at the short exposures that you're simulating here. There are trade-offs in the early observations of GRBs between going for short exposures to get good sampling of the light curve, for example, and being able to get through lots of filters, and having longer exposures to get sky limited. And I don't think that short exposures of 5 or 10 seconds will be sky limited. I think they'll be detector limited, and that will cost us detection efficiency. So I don't know if you've thought about that.
So supposedly the read noise normally is taken into account in the exposure time calculator that was used during the test. So the codes mainly were developed by David Corr, and these codes are including this ETC, which is the calculator which gives the magnitude and the SNR as measured by COLIBRI if it would have observed this a given GRB during given exposure time. And these computations are taking into account the read noise of the detectors. I mean, on the paper, this is what the code says. It is taken into account. So yes, normally the read noise is taken into account. But something to keep in mind is that the result I showed are made with very, how to say it, bright. Those GRBs are quite bright as GRBs. So they're like the good students of the class. So of course, if we test them, we have really good results, even with short exposure time. But that's why I suggested to stack images, as we mentioned with, as I mentioned before, the stacking of images could help have a better SNR, because of course with the dusty GRBs we would not detect it with only 5 or 10 seconds of exposure at the first measure.
No, but even if you stack, if your individual images are detector limited, you lose detection sensitivity.
Oh, okay.
So.
Okay. Thank you. There is another question. I think we have time for the second question from Veronique. What is the main limitation? Limited wavelength coverage or the SNR of the data?
It depends. I'm not sure to understand the question. It depends on which phase we're talking, or what is the main limitation? Veronique,
maybe you want to...
I would say it's the SNR of the data, because this is what makes detection or not detection, right? So the idea concerning the wavelength coverage for the estimation phase, it's important for us to have various bands. In terms of wavelengths coverage, it's better to have many bands on the estimation phase, because the more bands mean the more points to fit the curve, and then have a better estimation of the redshift.
Yes, can you hear me? My question was about the redshift.
Yeah, okay.
Yeah, so because you didn't discuss, well, it was very short, so you discussed the SNR and the different sensitivity, but if you have to make a choice about the number of wavelengths or the SNRs, could be interesting to have a, an idea of what to do.
I mean, in order, the SNR remains an important parameter because it means how much the quantity of light we collect. But if we look at this graph, we can see the number of bands with detection is also important because most of the points that are out of the line are points with mainly not 7 band detection if we exclude the zone on the corner of the graph under 3 redshift. Okay. But as soon as we have not a lot of detection, such as at the top of the graph, the square points, only 2 detection, only 1 detection, you don't have a good fitting. So the number of band that detect is also very important to have a better fitting.
Yes, but also the wavelengths, near infrared versus optical.
Yeah, yes,
okay.
Absolutely, yes.
I'm afraid we need to stop this discussion now, and because we have again 3 more talks. So I propose to switch now to the next talk by Leonardo Garcia. The evolution of several relativistic jets through the magnetized medium produced by the fusion of two neutron stars. So, and Leonardo, I will tell you when you have 3 minutes left.